Hey everyone, and welcome to This Explainer. Today, we're officially putting on our lab coats, grabbing our metaphorical magnifying glasses, and zooming way, way down into the atomic world of Chapter 2. We're going to investigate the secret hidden lives of acids, bases, and salts. Chemistry isn't just about memorizing a bunch of dry formulas. It's really about observing clues and figuring out the hidden rules of the universe. So get ready, because we are about to uncover exactly how these powerful chemicals behave, react, and completely transform right before our eyes.
All right, so let's dive into this with a pretty crucial question. You probably already know from everyday life that acids, like lemon juice, taste sour, and bases, like soap, well, they taste better. But in a science lab, we definitely cannot go around taste testing concentrated hydrochloric acid or sodium hydroxide. That is a massive, massive safety hazard. So how do we identify these mystery substances sitting in those glass beakers? Well, we use molecular informants. These are special substances that actually change their physical properties when they bump into an acid or a base. Let's see who these informants are.
What's really cool here is the sheer variety of these chemical informants, which in chemistry we call indicators. Looking at activity 2.1, we've got our visual indicators. There are natural ones like litmus, which is this purple dye extracted from a plant called lichen, and it turns red in acid and blue in a base. Turmeric is another great natural one. Have you ever noticed how a yellow curry stain on a white shirt turns this weird reddish-brown color when you scrub it with soap? That's because soap is a base. We also have synthetic, lab-made indicators like methyl orange and phenolphthalein. But then, look at activity 2.2. This brilliantly introduces something called olfactory indicators. Olfactory is just a fancy word for smell. Things like chopped onion, vanilla essence, and clove oil. Instead of changing color, they change their scent. If you add a strong base to a vanilla-soaked cloth, that sweet vanilla smell completely vanishes. Poof, gone. It's literally an invisible aromatic clue. Okay, let's move on to our first actual physical reaction and see how this all builds up in activity 2.3. I want you to picture this. You take a test tube filled with dilute sulfuric acid, and you drop in a few pieces of solid, silvery zinc granules. Almost instantly, you're going to see this fierce bubbling forming right on the surface of the zinc. But what is that gas? To find out, we trap it. We send it through a delivery tube and pass it into a soap solution to blow some bubbles. Now, if you bring a burning candle near those floating soap bubbles, pop. You hear this very distinct, tiny explosion. That signature pop sound, that is the ultimate proof that the invisible gas being born in that test tube is hydrogen gas. Let's pull out a virtual whiteboard for a second and look at what is actually happening at the atomic level here. Imagine dropping a microscopic magnifying glass right onto those zinc granules. You've got your zinc, which is Zn, and your sulfuric acid, which is H2SO4. What happens is the zinc essentially steps in, gently taps the hydrogen atoms on the shoulder, and kicks them right out so it can bond with the sulfate itself. Why do we write it specifically as ZnSO4 plus H2? Well, that's because of the law of conservation of mass. Think of chemistry like a perfectly balanced scale or a very strict baking recipe. Every single atom we start with has to be completely accounted for at the end. Look at the equation. One zinc atom goes in, one comes out. Two hydrogen atoms go in, two come out as that popping gas. They're really just dancing partners swapping places. So the big takeaway here is this beautiful, simple rule. Whenever an acid reacts with a metal, it forms a new compound called a salt, and it kicks out hydrogen gas. And honestly, it doesn't matter if you're using hydrochloric acid, nitric acid, or sulfuric acid. The metal is always going to displace the hydrogen. I know chemical equations can sometimes look a bit intimidating with all the letters and numbers, but I promise you they are just simple before and after snapshots of this exact rule playing out in real time. Now, a great detective is always going to ask, wait, does the opposite hold true? Do bases react with metals too? In activity 2.4, we actually test this. We take a strong base, sodium hydroxide, that's NaOH, and we add those same silvery zinc granules. Interestingly, this reaction needs a little bit of a push, so we actually have to warm the test tube up. But once we do, bubbles appear again. It forms a much more complex salt called sodium zincate. The formula for that is Na2ZnO2. And sure enough, it releases that popping hydrogen gas. But here is a vital clue to jot down in your mental notes. These kinds of reactions are not possible with all metals. You see, bases are just a little bit more picky about their dancing partners than acids are. All right, let's shift gears to activity 2.5. I like to call this one the carbonate bubble test. We take two test tubes. In the first one, we put some sodium carbonate. In the second, sodium hydrogen carbonate. Now, when we drop dilute hydrochloric acid into either of them, we don't just get a few lazy bubbles. We get brisk effervescence. I'm talking fierce fizzing. A gas is rapidly escaping the liquid, but this time it's not hydrogen. So what is it, and where did it even come from? Let's use our whiteboard again to visually trace these atoms step by step. We're starting with sodium carbonate, Na2CO3, and hydrochloric acid, HCl. The acid viciously attacks that carbonate structure. The sodium breaks off and pairs up immediately with the chlorine to form NaCl, which is just your regular everyday table salt. But we're still left with carbon, oxygen, and hydrogen floating around. So the hydrogen from the acid grabs onto some oxygen to form H2O, liquid water. And what is left over? CO2, carbon dioxide gas. Keeping our detective hats on, we just successfully tracked every single atom from a complex solid into a salt, a liquid, and a gas. And to balance our mass scale, since we clearly need 2 sodium atoms and 2 chlorine atoms, we just pop a big 2 in front of the HCl and the NaCl. Done. And that brilliantly illustrates our second major structural rule. You'll definitely want to etch this into your visual memory. Any metal carbonate or metal hydrogen carbonate, when it gets mixed with an acid, will absolutely always break apart to form 3 distinct things: a salt, liquid water, and that fizzing carbon dioxide gas. This rule right here is the absolute backbone for understanding how acids break down carbonate-based materials in the real world. Everything from a piece of classroom chalk to giant ancient marble statues. But wait, as chemical detectives, we don't just guess that the fizzing gas is carbon dioxide, we have to prove it. So we take that invisible gas and pass it through a solution of calcium hydroxide, which is commonly known as lime water. As the CO2 bubbles through this perfectly clear liquid, boom! The liquid suddenly turns completely milky. Why? Because the gas is reacting with the lime water to form calcium carbonate, CaCO3. And guess what? Calcium carbonate is literally chalk. Because it doesn't dissolve well in water, it appears as a solid white precipitate right there before our eyes. Okay, now we arrive at activity 2.6, which I absolutely love. It's what I call the ultimate cancel out. What happens when an unstoppable force meets an immovable object? What happens when you mix an acid directly with a base? Well, if we take a base and add a few drops of our trusty phenolphthalein indicator, the solution glows this super vibrant pink. But as we start dripping hydrochloric acid into it, drop by drop, slowly, suddenly that pink color completely vanishes. The solution goes perfectly colorless. The acid has entirely nullified the base. This brings us to what is probably the most beautiful foundational equation in chemistry. Base plus acid yields salt plus water. We call this a neutralization reaction. The harsh, biting, sour properties of the acid and the bitter, corrosive properties of the base, they completely dismantle one another. They cancel each other out entirely, leaving behind something totally new and far more gentle. Let's actually look at the specific symbolic equation from that cancel-out activity. We've got sodium hydroxide, NaOH, a very strong base, colliding head-on with hydrochloric acid, HCl, a very strong acid. Down at the microscopic level, the sodium pairs up with the chlorine, and the hydrogen pairs up with the hydroxide, the OH part. And the result? NaCl, which is literally the harmless edible table salt you put on your fries, and H2O, pure liquid water. It is absolutely wild to think that 2 highly hazardous lab chemicals can undergo a microscopic collision and produce the exact same salt and water you could find in a bowl of soup. Now get ready for the oxide plot twist in activity 2.7. We take a beaker with a small amount of copper oxide, which, by the way, is this stark jet black powder. Then we slowly stir in some dilute hydrochloric acid. I want you to visualize this physical color change because it's awesome. As you stir, that black powder entirely dissolves, and the clear liquid transforms into a stunning, vibrant blue-green. This striking color change is the visual proof that a brand new compound, copper-2 chloride, has just been formed. Now, let's connect the dots here. Think about what just happened with that copper oxide. A metal oxide reacted with an acid to form a salt and water. Wait a second, what else reacts with an acid to form a salt and water? A base. Therefore, chemistry is telling us that metallic oxides act just like bases. They are basic in nature. And the coolest part? It works perfectly in reverse, too. Remember the lime water test we did? Carbon dioxide, which is a non-metallic oxide, reacted with calcium hydroxide, which is a base, to form salt and water.
so non-metallic oxides act exactly like acids. It's this incredibly satisfying perfect symmetry of chemistry.
We've uncovered so many clues today about how acids and bases behave and transform. But before we wrap up, I want to leave you with a massive cliffhanger. Think about this. If you take completely dry hydrogen chloride gas and test it with completely dry blue litmus paper, absolutely nothing happens. No color change, nothing. But the very second you add a single drop of water, boom, it turns red. What is that invisible ingredient, water, actually doing to those molecules to make an acid truly act like an acid? Think about those ions breaking apart. I want you to ponder that mystery, chemical detectives, because that is exactly where we're going to pick up next time. Here's our roadmap for today. We'll start with a hidden spark in acids, see why water changes everything, explore the power of pH, meet the salt families, look at some everyday chemical superheroes, and finally ask, are crystals actually dry? Let's get right into it.
All right, part 1, the hidden spark in acids. Let's kick things off by zooming way down to the subatomic level. So what exactly makes an acid act like an acid? Picture this. We're doing activity 2.8 on a whiteboard. We've got a beaker, we stick 2 nails into a cork and place it right inside. Then we wire those nails up to a battery and a bulb to make a complete circuit. First up, we pour in some glucose solution. We check the bulb and, well, nothing. It's totally dark. But let's swap out that glucose. Let's pour in some dilute hydrochloric acid, or HCl, and boom, the bulb lights up brightly. So what's the takeaway here? For electricity to flow through a liquid, you need invisible charged particles called ions moving around. Glucose doesn't make them, but our acid, it absolutely does.
The specific particle doing the heavy lifting here, the secret ingredient in literally all acids, is the H+ cation. Whether it's hydrochloric acid, sulfuric acid, or acetic acid, they all pump out these tiny, positively charged hydrogen ions when they're in a solution. So the big takeaway is this. It's the production of these H+ ions that carries the electrical current. That's what gives acids their chemical superpowers.
Moving on to part 2, why water changes everything. Now, here is a massive plot twist for you. Acids actually can't do any of this stuff on their own. Let's look at activity 2.9 to prove it. If we react solid sodium chloride with concentrated sulfuric acid, we get HCl gas. Now, if we take a perfectly dry piece of blue litmus paper and hold it in that dry HCl gas, absolutely nothing happens. Zero color change. But the second we use a wet piece of blue litmus paper, it instantly turns red. This is a brilliant visualization showing us that the H+ ion simply cannot separate from the HCl molecule if there's no water around. Water is like the ultimate molecular crowbar needed to unlock an acid's power. Picture water molecules acting like tiny magnets. When HCl meets water, the water literally rips the hydrogen away from the chlorine. But here's the thing, hydrogen ions cannot exist on their own. They immediately grab onto the water molecules to form hydronium, which we write out as H3O+. So from here on out, whenever we think about acid in water, we've got to think of H+ aqueous, or the hydronium ion. Now, because water and acids interact so intensely, we have to be super careful. Think about activity 2.10. If we take water in a beaker, slowly add just a few drops of concentrated sulfuric acid, and then touch the bottom of the beaker, wow, it feels incredibly hot. Dissolving an acid or a base in water is a violently exothermic process, meaning it releases a massive amount of heat. This is exactly why you must always add acid slowly to water while constantly stirring it. Never the other way around. If you pour water directly into concentrated acid, the sudden blast of heat can actually cause the whole mixture to splash out and cause severe burns. So safety first. Which brings us to part 3, the power of pH. All right, so we know H+ ions are the true source of an acid's strength. But how do we actually measure them? Well, enter the pH scale. The P in pH stands for Potenz in German, which just means power. You can think of it like a ruler that measures the power of hydrogen, running from 0 all the way to 14. A dead center value of 7 is perfectly neutral, like pure drinking water. As you drop below 7, the solution gets more and more acidic, which means a higher concentration of hydronium ions. And as you go above 7, it becomes basic or alkaline, meaning you've got an increase in hydroxide or OH- ions. Now, why does this matter to you and me? Well, living things are incredibly pH sensitive. Our bodies usually operate in a super tight window between 7.0 and a 7.8. But let's look at your mouth for a second.
If the pH in your mouth drops below 5.5, usually because bacteria are eating leftover sugar and churning out acid, that acid actually starts dissolving your tooth enamel. Your enamel is literally the hardest substance in your entire body, and yet it gets corroded by this invisible chemical shift. Crazy, right?
And that leads us perfectly into our next big concept, neutralization. Have you ever been stung by a bee? It's the worst. The bee actually leaves behind an acid, methanoic acid, which causes that awful burning pain. But if you apply a mild base like baking soda right onto the sting, you get instant relief. Why? Because the base and the acid completely cancel each other out. The reaction between an acid and a base always gives us a salt and water.
Okay, let's jump to part 4, meet the salt families. Speaking of salts, let's explore the chemical children created when acids and bases react. If we look at activity 2.14, where we test the pH of different salts, we see something super interesting. Just like you inherit traits from your parents, salts inherit their chemical nature from the acid and base that formed them. If a strong acid reacts with a strong base, they perfectly cancel each other out, giving us a neutral salt with a pH of exactly 7. But if a strong acid reacts with a weak base, the acid kinda wins the tug of war, giving us an acidic salt with a pH below 7. And on the flip side, a weak acid reacting with a strong base gives us a basic salt with a pH above 7. Of course, the most famous neutral salt is sodium chloride, made from hydrochloric acid and sodium hydroxide. You probably know it as common table salt. It's so fundamental to human biology that it literally shaped history. It was a massive symbol of freedom during Mahatma Gandhi's Dandi March, protesting the unfair tax on a substance that every single human body needs just to survive. All right, part 5, everyday chemical superheroes. So, sodium chloride isn't just for making our food taste good. In the chemistry world, it's the raw starting material for some pretty incredible stuff. From it, we get baking soda, or sodium hydrogen carbonate. Since it's a mild, non-corrosive basic salt, it is the absolute perfect antacid to neutralize an upset stomach. Plus, it releases carbon dioxide when it gets heated up, which is literally the exact thing that makes your bread rise and get all soft and spongy. Then we also have washing soda, which is a fantastic cleaning agent for our homes and has the unique superpower of removing permanent hardness from water. It doesn't stop there. Using the chlorine gas we get from saltwater brine, we synthesize bleaching powder, which is an absolute lifesaver for purifying drinking water and killing germs. And out in nature, salt isn't always just those tiny white flakes on your dinner table. We literally mine massive, brown chunks, called rock salt, from giant beds that formed when ancient seas completely dried up millions of years ago. Finally, part 6. Are crystals actually dry? All right, time for our final mystery. Take a close look at a solid, seemingly dry salt crystal. Is it actually totally dry? Let's whiteboard activity 2.15 and find out. Imagine taking a few crystals of really beautiful bright blue copper sulfate and dropping them into a completely dry boiling tube. We hold it over a flame, and as it heats up, something wild happens. The crystals lose their blue color entirely and turn stark white. And look up near the top, cooler part of the test tube. Water droplets have just appeared. Where on earth did they come from? The crystals themselves. If we take that white powder and just add a couple drops of water right back into it, the bright blue color magically returns in a flash. So this proves that those solid, supposedly dry crystals were actually holding water trapped inside their atomic structure the entire time. We call this hidden moisture the water of crystallization. It's a fixed number of water molecules locked into one formula unit of a salt. It acts kind of like an atomic-level sponge that gives certain salts their specific geometric shape and their bright colors. Copper sulfate, for example, has exactly 5 water molecules locked inside its structure. And this exact science gives us one of our most important medical tools, plaster of Paris. When you buy plaster of Paris, it's just a white powder, calcium sulfate hemihydrate. But when a doctor mixes it with water, it rapidly locks those water molecules right back into its crystal structure, turning into a hard solid called gypsum. This is exactly how doctors create a rigid, perfectly molded cast to support a fractured bone and let it heal in the exact right position. We have covered some incredible ground today, from the subatomic spark of hydrogen ions to the hidden water trapped inside solid crystals. Before we wrap up this explainer, let's leave off with a quick challenge straight from your textbook exercises to test your new mastery of neutralization.
Think about this. If 10 milliliters of a basic sodium hydroxide solution is completely neutralized by 8 milliliters of our hydrochloric acid, what volume of that exact same acid would you need if you doubled the base to 20 milliliters? Take a second, balance the logic in your head just like a chemical equation, and keep exploring the amazing chemistry all around you. See you next time.
All right, welcome to your Ultimate Exam Cracking Masterclass. In this explainer, we're looking directly at the official KSEAB key answers to make sure you secure maximum marks on Chapter 2, Acids, Bases, and Salts. If you're a 10th standard student gearing up for the Karnataka SSLC board exams, you already know the basic science concepts. But look, knowing the science and knowing how to extract every single mark from the examiner are two completely different games. Today, we're putting on the hat of the veteran evaluator. We are going to look at exactly where students bleed half marks and exactly what the examiners are dying to see written on your paper.
So here is our KCEB blueprint for today. 1. The evaluator's blueprint. 2. Hacking 1-mark MCQs. 3. The 2-mark equation traps. 4. Cracking the pH scale. And 5. Scoring big on salts. We're focusing strictly on high-yield sections, so let's get right to it.
Let's dive right in with a massive reality check. Have you ever walked out of the exam hall feeling like you absolutely nailed a chemical equation, only to get your paper back and see you lost half a mark? Well, an evaluator looks at your paper, sees a missing physical state, forgetting that little S for solid, or AQ for aqueous, or an unbalanced coefficient, and boom, half mark gone, instantly. So we're fixing that habit right now. When you practice tonight, every single equation needs its physical states, period.
Section 1. The Evaluator's Blueprint. Understanding KSEAB Fractional Scoring. We are going to look strictly at the official evaluation rubrics to see exactly where marks are awarded and where those sneaky mark traps are hidden.
Section 2. Hacking 1-mark MCQs, Speed, Precision, and Mark Traps. These 1-mark direct questions are an absolute favorite for examiners to test your conceptual clarity under pressure.
Okay, look at this massive mark trap right here. The question asks, as the pH value of a neutral solution increases, what happens to its properties? Now, a lot of students completely rush this. They misread the relationship between pH, acidity, and basicity. They see the word increases and just immediately jump to totally wrong conclusions about hydrogen ions.
But here is what the official key actually demands. When that pH goes up past neutral 7, it's becoming a base, right? Therefore, the basic property increases, and, this is crucial, the number of OH- ions increases. That is straight from the official answer key. Do not get tangled up in H+ ions here. Keep it simple. Higher pH means more basic, which literally means more hydroxide ions.
All right, here's another trick question. How do you detect a base using blue litmus paper? This is a 1-mark trap where students routinely bleed points just by overthinking and trying to invent a color change that doesn't even happen.
Look, an acid turns blue litmus red. We know that. But a base? A base does absolutely nothing to blue litmus paper. Do not write that it turns blue, because, well, it was already blue. You need to write exactly that the color does not change to secure your full mark. The evaluator is specifically scanning your answer for the words does not change. That's your golden ticket.
Moving on to Section 3, the 2-mark equation traps, navigating reactions and observations. Now we enter the 2-mark territory, which is basically a complete minefield of common student mistakes. So think about this classic setup. When an acid reacts with a metal, it liberates hydrogen gas. But just writing the equation is not going to cut it for full marks. Evaluators absolutely love asking how you test for this gas. You have to confirm it visually with the bubbles and audibly with that classic pop sound. Bringing a burning candle near the gas bubbles to hear that pop, that is a mandatory observation if you want full marks when describing this activity.
Now I want you to lock this brilliantly simple conceptual shortcut into your brain. Keep this matrix handy. Metallic oxides act like bases, and non-metallic oxides act like acids. Notice how they both yield salt and water? It's essentially just a neutralization reaction wearing a disguise. So, if the board asks you to prove the nature of a metallic oxide, you just write out its reaction with an acid, show the salt and water products, and boom, 2 marks in the bag.
Okay. Here's another specific concept the examiners love pulling from the dark corners of the textbook: partial dissociation. If they throw a question at you asking to identify compounds that dissociate partially in aqueous solutions, they are totally just testing if you know your weak acids. Your brain should immediately jump to carbonic acid or phosphoric acid to bag that easy mark.
Section 4.
Cracking the pH scale, the 3-mark application heavyweight. Let's escalate to a really heavy-hitting 3-mark application question, straight from a recent model paper.
So, you're given 4 unknown solutions, A, B, C, and D, with their respective pH values, 5, 2, 7, and 11. You're asked to identify 3 specific properties based solely on these numbers. Now, don't panic when you see application questions like this. Honestly, they are some of the easiest points on the entire paper if you just apply the basic rules of the scale.
Right from the evaluator's desk, here is exactly how those 3 marks are split up. 1 mark for identifying solution B is having the most hydronium ions, because remember, the lower the pH, the higher the acidic strength and hydronium concentration. 1 mark for identifying solution C as neutral, since it's dead on 7, and 1 mark for identifying solution A as the weak acid, because a pH of 5 is acidic but way closer to neutral than the strong acid down at pH 2. 3 simple letters, 3 massive marks.
Finally, Section 5, Scoring Big on Salts, Formulas, Uses, and Definitions. Listen, this section is an absolute mark magnet, but only if you memorize the exact formulas and uses required by the board. Pay super close attention to the precision required right here. Memorize this definition exactly as written, the fixed number of water molecules present in 1 formula unit of a salt. This is a guaranteed fast mark, but evaluators are looking for it word for word. If you just write water inside a crystal, you are getting a 0. Use the board's exact vocabulary, fixed number, water molecules, 1 formula unit.
Take a look at this official breakdown from the key answers. Notice how you earn a half mark just for remembering the exact chemical formula, and another half mark for each use. For plaster of Paris, that .half H2O is absolutely critical. If you write a full H2O, you lose the mark. And for baking soda, NaHCO3, remember it's an antacid and it's used in fire extinguishers. Whatever you do, do not mix up the uses of washing soda and baking soda. That is a trap students fall into literally every single year.
When you're tackling the chlor-alkali process, which is a huge board favorite, sequence your products super clearly like this. 1. Sodium hydroxide. 2. Chlorine gas. 3. Hydrogen gas. Listing them out cleanly stops you from blurring them together under exam pressure, and it makes it ridiculously easy for the evaluator to just go check, 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 and hand you your full marks.
As you're reviewing this chapter tonight, I want you to grab your textbook, look really closely at Activity 2.15, and ask yourself this final vital question. Are the crystals of salts really dry? Think about it. What exact color change happens when blue copper sulfate crystals get heated up in a boiling tube? Why do they suddenly turn white? And what happens when you drip a little water back onto them? Master the actual mechanism behind this color change, and you are going to secure those final tough marks. But let me leave you with this. If heating removes the water of crystallization to make the salt white, what happens if you leave those completely dehydrated crystals sitting out in the open air during monsoon season? Will the board ask you about that reverse reaction tomorrow? You better be ready for it.